Hello, musical scientists! Welcome to another episode of Science Life. It's been a long time since we did one of these, about a year, in fact, but I'm bringing it back. If you enjoyed the recent Nanobot video, and if you haven't seen it, go and watch it, I think, because the video that you're about to see, or podcast, if you're listening to this on audio, is a conversation that I had with Professor David Leigh. Professor David Leigh is the chair of chemistry at Manchester University, and he's one of the forerunners in the field of synthetic molecular machines and molecular robotics. A lot of the little gizmos that you saw in that video were products of Professor Leigh's lab. And so I'm very excited to talk to him, and it was a fascinating conversation. We start out more with what's going on in the field of molecular robotics and his views on nanotechnology, but we diverge into creativity and open science and how to think about finding connections between different fields and this sort of new connected world that we're trying to build within science that he and I really seem to have a connection with. So I hope you enjoy, and without further ado, I bring you my conversation with Professor David Leigh.
We're the spice. We're the flavor of the universe.
Mystery, harmony, da-da-da-da-da, science life.
All right, I'm here with Dave Leigh. Hi, Dave.
Hi, Tim. Hi, everyone.
Yeah, it's good to have you on the show.
Thanks a lot for having me.
You're the person who kind of made this entire thing happen, I suppose. You were really the inspiration reaching out to me to go out and research this field of molecular robotics. Maybe we could start by you just telling us a little bit about yourself. Who are you? How did you get to where you are now? What was your path?
Oh, wow. Well, I did my PhD in an area called supramolecular chemistry, which is about how molecules interact with each other. And after that, my PhD was actually with Fraser Stoddart, who recently shared the Nobel Prize for synthetic molecular machines with
right.
Ben Ferringer and Jean-Pierre Sauvage. Yeah,
that was
but I was actually in his group. Sorry,
that was 2015. That was the Nobel Prize in chemistry.
2016.
2016.
The 26th Nobel Prize for chemistry. I was actually in Fraser's group before he started working in that field as well. And then when I started my independent research career a few years later, we had just a serendipitous discovery. Something unusual happened in the lab, as so many projects start from. We discovered a new way of making mechanically interlocked rings. And Fraser and Jean-Pierre Sauvage had shown a few years earlier that these architectures could be useful as the basis for perhaps beginning to make very simple molecular machines, because they allow large amplitude, big motions to occur. And if you can control that, maybe you can use that as a basis of molecular machines. So we just stumbled into the area, but I guess we were well prepared to go on.
Right, yeah. So these, I tried to show as much of that as possible in the video. So
and you did a fantastic job.
So yeah. It's really these interlocking, what you call mechanical bonds, right?
This mechanical bonds. Catenane, from the Latin catena, meaning chain, because they're like links of a chain. And the other sort of molecules are called rotaxanes, where you have a ring that's threaded onto an axle. And the nice things about these molecules and what Fraser and Jean-Pierre showed in the 80s and 90s is that you can control the motion of those components and actually switch them between different positions. And we took that basic concept and then tried to make more sophisticated systems, try and use that motion to do interesting things and to make pumps and motors and even what's becoming known as molecular robotics.
All right. I do want to talk more about that, but I'd like to know a little more about you first, because I think from what I know of you, you've got a fairly broad range of interests, and you're a little bit like me, it seems, where your interest flies all over the place. So
yeah, I think that science is a creative endeavor, and the best science comes from creativity. So there's a lot of different things that sort of float my boat that I'm interested in. All sorts of science communication. I love the sort of things you do, which is why I was glad that we were able to persuade you to get involved and do such a great job. And lots of other things as well. I mean, I had a background as a bridge player. So I used to play cards probably a bit too much when I was a student, and then during my PhD I actually had to decide whether to turn pro, in which case I'd probably be a poker player now, and I decided not to do that and decided to carry on with science. But it means that I know my way around a pack of cards, and again I've tended to use that in various aspects of my job as well. So I like to use magic in my lectures and show on. I think that that's again an entertaining way to present difficult concepts to a scientific audience. So
you use magic in your lectures and stuff?
Yeah, sure. Yeah. So I think that magic has a lot to show scientists. I mean, obviously there are differences. Science is all about explaining what's real, and magic. Obviously, there's a little bit of what you're showing is not real. There's something else going on. But I think it's a good lesson for scientists to learn from magic, because when we do science, when we do experiments in the lab, you know what goes into the experiment. And you can see the data that comes out, and then on the basis of that, you draw a line and say, okay, so this happens, that happens, that happens, and that happens. And magic is a nice reminder that just because you know the physical setup at the start, or you think you do, and just though you know the outcome at the end, you really don't know what's happening at the nanoscale and in the during the experiment, and maybe things are going on that you don't expect and you don't know about. And so the simplest explanation is not the only one that might be possible. And that's a good thing for scientists to remember, I think.
Right, that there's kind of, when you get into what you're working with, I guess, which is it's more complexity. Like what I started doing, sure. I was in fundamental physics when I was in school. So it was really about go down to the lowest layer possible and try to get under it and see what's simpler than that, and what's simpler than that, what everything's based on.
Yeah.
But what you're doing is more like you've got the tools now, you've got the laws of physics, but the possibilities of what you could build with this thing, it does sort of seem like magic, I guess. Like you've got this 52 card deck, and that's what you have. But within that, just the combinatorial possibilities are immense.
Well, so, I mean, chemistry and synthetic chemistry, the sort of things that we do, is all about creativity. You understand the tools of how to put molecules together, and there's been 150 years of building up that level of science, so that we know how to put these Lego bricks of elements and fragments of molecules together. The question now is, what should we build, and why? And molecular machines gives you an opportunity to perhaps change the way that things are currently done, and to start a new sort of technology built from the ultimate in miniaturization, which is building machines out of molecules. And
so when you're figuring out what to do next as a chemist in this sort of creative process, how does that work? Where do the ideas come from for what to try next?
In our group, all the ideas come from the students trying to go further and further of what's been possible before, and it's always building on layers. So catenanes and rotaxanes were just the start, and this ability to make switches. but that's really just they're the simplest sort of machines that you can get. And just as in the Middle Ages, engineers and scientists realized that there were a certain number of fundamental machines, such as the lever and the pulley and so on. The engineers then realized that you could make more complex machines by combining the functions of simple machines together. And enables them to do things that you can't do just with the simple machines. And that's how you build this technology. We have the very simple basic building blocks and machines that have been established now in chemistry. And it's all about learning how to combine those sorts of machines to do more complex tasks that you can't do any other way. And it's not like it's a molecular engineering, but we can't just follow the rules of engineering from the big world because, of course, the way that matter behaves at different length scales is just so different. So engineering techniques just don't scale down. And so we have to come up with new ways to do engineering at the molecular level.
Yeah, let's get into that a little bit, because I think one of the things that I was able to briefly mention in the video, but it's a concept that I find is hard to wrap your head around, and maybe you can give your own sort of take on it as an explanation, is this idea of this information ratchet mechanism, or like all these different ratchet mechanisms. So you've got a system that's very down at that scale, is jostling around and moving every which way, but you have a force. It's like a statistical force. It's not even really a true force, but it's sort of a numbers game over time, that if you apply certain inequalities to different parts of the system, you can get it on average moving in a particular direction.
Yeah.
So how would you explain what an information ratchet is and how it works?
Right. So the big difference between machines in the big world, or the way matter behaves in the big world, and the small world, is that at the nanoscale, everything is constantly moving through random thermal motion or Brownian motion. And it's also very sticky. So that's, again, a big difference to the big world, and another reason that you can't just shrink engineering concepts down. So all the elements that we use to build machines in the big world, the Newtonian mechanics, things like momentum and inertia, those things become irrelevant at molecular length scales. If you give a protein a push, it'll stop immediately in a cell. So you have to use, instead of Newtonian mechanics, you have to use statistical mechanisms in order to get to control motion. So it's not getting things to move. That's the difficult thing at the nanoscale. It's controlling the directionality of all the motion that's going on, basically cutting out all the motion that you don't want, and then that just leaves you the motion that you do want. And the way that that's done is using ratchet mechanisms, Brownian ratchet mechanisms, and these are the general solutions to how to make motors in the molecular world, and the key to making any kind of sophisticated machine.
So how would you describe a Brownian ratchet mechanism?
Yeah. So again, the idea for these sort of things, or the realization of them, actually dates right back to when the laws of thermodynamics were being formulated, and James Clerk Maxwell, the famous Scottish physicist who was responsible with Boltzmann for the theory of heat, and was also involved in some of the laws of thermodynamics being formulated, realized that there was a sort of a conundrum between the theory of heat and the laws of thermodynamics. And he illustrated this in a thought experiment called Maxwell's demon, which is where you have a load of gas molecules in a box with a compartment between them and a trap door. And Maxwell proposed that there would be a being that's come to be known as Maxwell's demon that could open this trap door to let through molecules that were fast moving or hot from one side to the other, and stop molecules that were slow moving or cold from moving in the same direction. And so Maxwell realized that you could use that to sort molecules into hot and hot and cold, fast and moving and slow moving. And if this door was frictionless, it looks like the being expends no energy to make this happen. And yet at the end, you've got a heat gradient between the two sides, hot molecules on one, cold molecules on the other. And of course, Maxwell realized you can use a heat gradient to drive a turbine and to do work. And if you've expended no energy to open and close the door, and you've got energy out at the end, you can have a perpetual motion machine and limit the supply of energy, but unfortunately break the second law of thermodynamics. So it took physicists maybe 50 years to realize that the solution to this paradox is, of course, the being has to process information to know when to open and close the door. And that's always costs more energy, the processing of information, than it's possible to get back. But that process of opening and closing the door and trapping the hot molecules on one side and the cold molecules on the other, and setting up an energy gradient, that's what ratcheting is. And so that thought experiment was really the first time that the proposal for a molecular motor or a mechanism for a molecular motor was sort of envisaged, although, of course, Maxwell didn't see it that way, of course, at the time.
So your machine is basically acting as Maxwell's demon, but you're giving it some sort of additional energy that allows it to not break the second law of thermodynamics? Yeah,
that's exactly right. You have to put in more energy than you get out in order not to break the second law, but the principle is the same. You're telling the molecule to open a door or to have faster kinetics in one direction, and then once it's got to that part, it's using the information of its position to tell the system to stop it being able to go back, to shutting the door behind it. And that leads then, just through the random thermal motion of the components being able to move back and forth through the door, it shuts when you want it to, so that the particles can't go back, and it just drives them inexorably in the direction you want. And you're able then to use that to do productive things and to use them as motors or pumps or synthesizing machines, as you showed.
So an information ratchet, say you've got a pump that you're trying to bring something from one side of a membrane to another. You have the species that you're trying to get across, and the information you're talking about is the information of the molecule itself being close enough to the pump to change it in some way?
Yeah, that's exactly how it works. So there's in effect a signaling of the position of the particle to the pump that tells the pump, okay, shut the door behind me so that I can't go backwards, and then I'll have to go forward. That's exactly how it works, and how we try and design these sort of things. But of course, there already are the other inspiration from this, besides coming from the fundamental laws of physics, are of course from biology, because this is exactly how biological pumps work.
Yeah, this is something that evolution beat us to by billions of years, how to make these little ratchet pumps and molecular motors.
Yeah, that's exactly right. So what we try and do is learn from both the fundamental laws of physics and what physicists have learned about how to design ratchet mechanisms, and then we apply those principles as the basic mechanism to make very simple chemical systems, because biological systems are really, really complicated the way that they go about doing these things, or the structures are very complicated. We make very minimalist structures that just have the elements that are needed in order to drive the physics in the way that we want. But then that also explains how the biology works. Mm-hmm. So it's kind of a nice circle.
Yeah, and it seems to me like that biology, because what you're doing, like your approach to nanotechnology is kind of this bottom-up approach, right? Where it's you're starting with basic chemistry and then trying to build more and more complicated molecules out of that until you get something that's a really functional machine. And what's cool to me about biology is it's kind of a proof of concept for your entire philosophy of how to do nanotechnology. It's sort of proof that from basic chemistry, you can get all the way up to macroscopic molecular machines, right?
Yeah, that's absolutely right. It's the evidence that that nanotechnology works. That's what life is. The other way that people originally thought about approaching this, and most famously in Firemans' lecture, "There's Plenty of Room at the Bottom," is this sort of top-down idea of trying to take engineering concepts from the big world and apply them. For example, the manipulation of atoms by other molecular sort of systems that are so macroscopic machines.
The idea being that you make a large tool that makes a smaller tool that makes a smaller tool that you work down to the molecular level.
And so that's superficially attractive because we know, of course, that how mechanics works in the big world. But the problem is, as we discussed earlier, the way that matter behaves at the small level is just so different that it doesn't make sense to try and make machines that work in the same way as they do in the big world. If you always have to design a machine according to the environment that it's going to work in. So if you want something to move along a solid surface, a road in the big world, you'll have a car with wheels, and you'll transfer angular momentum from the camshaft to the wheels and use that angular momentum to a projector on the road. But even if you change that road from being solid to being a liquid, put it on water, and that mechanism of the machine is completely useless, then you need a hull of a boat, and you need a sail or a propeller to drive it along. Change the environment again, lift that machine up in the air, and the sailing boat becomes useless. Then you need an aeroplane with wings and a jet engine, take it up into space. That mechanism doesn't work. Then you need rockets, and that's all in the big world. The molecular world is so very different in the way that matter behaves that trying to develop those sort of machine concepts and shrinking them down to the molecular world just doesn't make any sense. It seems to make much more sense to learn how biology solves the conundrum of how do you make machines that work at the nanoscale, and apply those ideas, those concepts and those techniques to the design of synthetic molecular machines. And the advantage that we have over biology is, of course, biology is limited to just 20 amino acid building blocks, which it uses for all the motor proteins and machines in the cell. But we've got the whole periodic table and 150 years of chemistry to try and design new things. But it takes time because, as you pointed out, biology's had 3.5 billion years of evolution to get it right. And, we've been going maybe 20 years. Yeah.
But that gives me sort of two questions to ask you. The one is what can biology still do that we can't, which is maybe there are a lot of things. But the other question is, what do you think that specifically this sort of technology could be able to do that the random processes of evolution haven't been able to do more effectively?
Yeah. Okay, so the first one first. I mean, biology can do loads and loads of things that we can't even begin to do yet with synthetic molecular machines. I mean, all of life. But just one example, the ribosome, which is the thing that takes genetic information, the information including genetic information through strands of messenger RNA. That encodes for the amino acid sequence that occurs in proteins. And the ribosome is the molecular machine that reads this tape of information and then adds the building blocks in the sequence that the amino acid building blocks in the sequence that the genetic code tells it in order to make all your proteins. So that's an example of a molecular machine building a sequence polymer. And it underpins all of life. We've started to make, chemists have started to make just the very simplest examples of those, but all we can put together is 3 or 4 or 5 amino acids in sequence. The ribosome puts together 20 amino acids every second in a strip that can be 200 amino acids long. and it's far more efficient and effective. And we don't know how to do that for any other building block than biology already uses. The second part of your sorry, Tim, I've forgotten. What was the second question?
The second question was, what do you think that these synthetic molecular machines have the capacity to do that hasn't been reached by biology?
Yeah, so of course evolution just takes you down a kinetic bottleneck. So once evolution solves a particular problem through a mutation, there's not necessarily any advantage for it going back and finding a better solution that would require many more modifications to the genetic code. That would be a very unlikely thing to happen if there's no evolutionary pressure for that to happen. So generally, biology is always going to produce something that works, but down a kinetic track, the easiest way, or statistically just the way that it did evolve. So as chemists or as scientists, once we can obviously use our imaginations and our creativity and the whole of chemistry that's being developed and has been developed and the whole of the periodic table to choose what are going to be the best ways to solve a particular problem. And as an example of the way that you can come up with different solutions to different problems, if biology was the only way of doing things, then the computer that we're seeing each other on would be wet and made of organic matter like our brains. Right. But it's not. It's scientists designed it to, and engineers designed it to work in a different way, using a completely different kind of technology. So it doesn't always have to be biomimetic or using the same solutions that biology does to get to a good technological answer. But from the machines sort of side, because we don't know how to make molecular machines, or not complicated ones yet, it seems to make sense to learn the fundamental rules of the game from biology, make the switches, make the motors, make the pumps, make the logic gates, that see how biology uses those, and start to make much simpler versions in the laboratory. And again, there's an example in chemistry of where that's been very successful, and that's making catalysts. So catalysts are things that chemists use and industry uses to make all kinds of drugs, to accelerate chemical reactions or to make reactions occur that really don't want to, that are really slow. 20, 30 years ago, there was no way to do that in a really effective way. But biology has enzymes. That's what enzymes do. They're biological catalysts, and they accelerate all the kinds of reactions that you need in the cell. But they're proteins, and so they are enormous molecules of can be 100,000 Daltons, so 100 or 200 amino acids in a big long chain. But chemists aren't limited to using amino acids. They're not limited to using water and ambient temperatures and pressures. So chemists over the last 20, 30 years have made catalysts that can catalyze reactions that enzymes can't, that can be faster, that can be more specific, but by using different elements. And they're much, much smaller than the enzymes that biology makes. And so that's just one example of the way that chemists can do things by learning the rules first, often from biology, that having the whole periodic table and not being limited to biological building blocks, we can do things that are more effective and more useful.
But a lot of the time, what we still do is that we'll do an interface between the biological and the mechanical. Right? If you talk about a lot of food processes, that we're still using bacteria or yeasts. Or,
absolutely. And that's another, molecular machines is absolutely no exception. First of all, you've got synthetic biology, where people are taking synthetic biological machine parts that already work, and then using them, putting them together in different ways, again, to making new kinds of molecular machines that biology doesn't make. But it's like taking the wheels from one one enzyme or one bacteria and taking the chassis from another, putting them together to do different kinds of things. And then there's also this wonderful building block called DNA. So
Right.
DNA is used by biology, of course, to pass down genetic information. But for a scientist, it's also a fantastic structural tool, because all the interactions that are used for passing down information, the encoding that's in the base pairs, that recognition can be used to get very, very selective interactions between strands, to build them up and use them as molecular machines and as molecular materials that are extremely well behaved and can be understood in a very simple way and programmed to operate in new kinds of ways that completely unbiological like.
Yeah, like I guess biology has been evolution has been this very slow algorithm, but at the same time it has worked out a lot of the basic building blocks that are very stable and very versatile, right?
Yeah, I mean, yes, that's true. But and so scientists can use that to our advantage, because a lot of the things that biology does, we haven't found better ways of doing it. So we haven't found better ways of encoding information than DNA base pairs. I mean, that's an exquisite example of fidelity, of which base pair recognizes another base pair, together with being relatively weak that you can strip them apart. If the binding was too strong, it would be less useful, and you wouldn't be able to strip it apart in the cell to pass on the genetic information important for replication. But there are other sort of things where we can make reagents and catalysts and reactive molecules that can do things that are better than biology. And we're not restricted to having to work in water and at room temperature. And that can have lots of advantages, as I say, for example, in drug manufacture or making polymers or other kinds of materials. So it's learning from biology, sometimes just naked stealing of biological parts and concepts, but also realizing that we can go beyond that in our design principles by using our creativity.
Yeah. So when I made the video, what I kind of found was that it's obviously a field that's only a couple decades old, and it felt like what I was doing was, it was a little bit scattershot, right? Like I had to sort of pull all these different examples from all over, and it is at the stage of, here are the basic building blocks that we're figuring out. But I saw a quote by Ben Feringa who was saying, now we have 20 different little rotational motors that all work in slightly different ways. Now's the time to start using these elements and going to the next stage and seeing if we can actually build complicated machines. So what's the state of the field now?
Yeah, no, I think that's exactly right. We have those basic gizmos, if you like, that have been made, and now the task is to take these simple machines and to make what, again, a medieval engineer would call compound machines, where you're combining these machine elements to make something that's more sophisticated and can do something that's more than the sum of its parts. So, for example, we're starting to make things that can really be seen as the starts of molecular robotic systems that can be programmed to do different tasks, to build different structures, depending upon the information that you feed into it. And that's possible by mixing together different components, switches, binding units, motors, ratchet mechanisms, by putting them in the right sort of order and having the one machine doing one part of the machine doing one thing, another part of the machine doing another. You get something that's more than the sum of its parts, just like a watch or something like that in the big world, which has springs and cogs and hands and so on, where every part does a different part. That's what we're trying to begin to do with the synthetic molecular machines, and particularly in this area of molecular robotics and programmable molecular machines.
Yeah, so one of the machines that your team made is one of the ones that shows up in the video. where if the viewers have seen the video, they'll remember a machine. It comes by very quickly because a lot of stuff in that video happens really fast. But it's got a base and it's got a switching hinge that goes from one direction to another. And this is a machine that can produce all 4 like stereoisomers of a given chemical.
Yeah, that's right. So it can build different molecules depending upon how you program it. And I mean, it's a really small and simple molecule, way simpler than a biological enzyme that would that can do similar sorts of things, that can do multi-stage synthesis. This is much, much smaller. But it consists of a lot of different working parts going on in that molecule. You've got a platform with different catalytic groups that can cause chemical reactions to occur on it. You've got a switchable arm that can be switched from the 2 sides. The arm's got a gripper attached to it that can be used to pick up a substrate molecule. And so you can hold this substrate molecule over one reactive side, or you can switch it to another reactive side, and then you can get it to do multiple chemical reactions. So by controlling which reaction happens next and where the position of the arm is, then you can use that to build a different product. And this is very reminiscent of what's done in factories for building a car. You have robotic arms that pick up pieces and sticks them together, and you can program those arms to do different things, to change the car that's being made or the parts that are being put together. And this is the same sort of thing that we're now learning how to do with molecular sized systems that one day could be molecular factories, the basis of molecular factories.
So I want to ask you more questions. Are there sheep in the background? Do you live out in the country?
Yeah, sorry, we live on a farm. Sorry, that's coming. They seem to be hungry at the moment.
That's great. So you live? Are those sheep yours? Do you care for them?
No, they're the farmers. But they're only about 12 feet away. They're in the next field. If I could switch the computer around, I'd show you. But yeah, sorry, I've got the door open because it's an unusually hot day in Manchester. You don't get many.
No, that's great. I've been wondering myself about moving out into if I could move out into the country somewhere, because right now I live in a basement in the middle of the city, and it's the kind of thing, with my job I could take it anywhere if I wanted to.
No, it's great. Very lucky.
Yeah. Do you find that the environment that you're in affects the way you think and the way you work?
Yeah. So that's actually the reason why, I run a lab in Manchester, which is a big city of maybe 3 million people. But I live outside on a farm about 15 miles away, and I do that because I like the quiet and the calm of the countryside. It lets me think. We can't have a lab here, and my group, who are much younger than me, definitely enjoy the city life. But for me, I definitely find it a way of being able to think and relax at the same time. Yeah,
I've been noticing that too. That if I just to change where I am or what I'm looking at, or to see green and go out somewhere, it'll jog my brain, and all of a sudden different ideas will suddenly connect that I've been stuck with for a long time. Yeah. I think that's important in creative professions like we both have. I want to go back to your magic for a little bit. Do you find that like having these other interests, like with magic and bridge, and I hear that you're an avid rock fan. Do you find that these different things, do they give you different ways of looking at things? Do they present you ideas that you wouldn't have had otherwise?
Of course. Of course. Yeah, I mean, they're different creative outlets and also inputs for what one does. So, I mean, the magic and is definitely about creativity and storytelling. So I find that useful in lectures as well. That that it's a way of telling a story in a different way and getting people to just think in different ways about things. Bridge is a game that's all to do with mastery of probabilities and statistics, which again leads, it's related to the way of thinking statistically about how machines work and those sort of mechanisms. It's not that I don't find that there's direct overlap, but I just think it's good for tweaking different parts of the brain. And I like all kinds of art, music, and all those sorts of things can be useful for work. A lot of the molecules that we make are aesthetically very beautiful, and I think that we like to make in our group things that are as simple as they can be, but no simpler. And that's nice because they're really minimalist in showing the function that they want to do. There's not extra parts strapped on to them that aren't necessary. And I think that that's, again, useful for explaining the concepts and getting that over, the concepts that we want to show through our work.
Yeah, like the thing is with creativity, it's such a mysterious force, right? Like where ideas come from is not something that's apparent to you, the person who is having the ideas. Even though we talk about being self-aware, there's a very limited surface level that we're actually aware of. So I often wonder, like, if I get a brand new idea, I don't know if you've ever had the experience of dreaming up an idea, but I know that's something, in the history of chemistry, there's some very prominent examples of solutions being posed in dreams. And I've always been it's very curious to me because it suggests that there's all this calculation, like there's more intelligence in you than you actually have conscious access to.
Yeah, no, I'm sure that's true. So the way that I like to approach problems is that I'll think about it hard, and then I leave it and let it mull around me. I don't get upset that I haven't figured out the answer and frustrated by that, because I'm then happy to go and do something else, and it can be magic or music or whatever, and it'll just be there in the background ticking over, or it can be other chemistry, and you'll just mull it over and then come back to it from a slightly different angle. And I find that that's a very good way for me of analysing problems and also of making decisions. So if I've got a decision that I have to make, I'll come up with what I think is the right decision, and then I'll just leave it and then come back to it. Was that really right? Let's look at it another way. Thinking about it either days later or while I'm doing some other things. And definitely at night is a good way of, whatever your brain does or at night, it's definitely a good way of coming up with interesting things. But then write them down. That's my top tip. Have a pen and paper by the bed just in case.
Yeah, I often think of it as sort of priming your brain, because I'll do that all the time too. A lot of my projects will start off as a rough draft, maybe 2 years before they get finished. And because I'll have an initial idea and then it'll just stagnate at some point. But then if you've already done that amount of work, then all the information that comes in from the next
it's not wasted.
year,
That's right.
and it's an incredible amount of information, right? And your brain is throwing most information away most of the time. But if you've got this problem just in the side of your brain somewhere, then there's different information that piques your attention. That thing that would have completely gone out of your head.
That's exactly it. I think you put it perfectly. It's priming your brain for whatever the project is going to be, or the ultimate idea. And I also agree totally that then you become more receptive to things from the outside. I'll be in a lecture and I'll realize, something that is being said normally I wouldn't have paid any attention to, and suddenly it'll hit me. Oh, that's a really interesting solution or way of looking at this problem or issue. So I think that that's absolutely right, and I'm sure that that's applicable to many areas of advancement that involve ideas and originality.
I'm no expert in this. I'm just sort of an observer of how a single creative mind works. Do you have any?
have no idea how you could do that. I mean, do the songs come first, and that you say, "Oh, I want to take"? I'm turning around and be the questioner here, but is it?
Oh, that's fine. I'm happy to talk about what I do.
Havana comes first, and then you think that that Havana Nana maybe we use that, or I mean, how on earth do you select the song? They work so great.
It's a complicated process. My first criterion to do a song is that I have to like it, because I'm going to be working on a project for months at a time. If I don't like the song that I'm doing, then it's just it demotivates you so much. It's surprising how much time you can waste if you don't like what you're working on.
Right.
So that's my first criterion. I have to really like it, and then it's honestly just about ideas a lot of the time. But often I'll let things percolate, like you're saying. So I'll have a list of topics that I want to cover, and then I'll have a list of songs that I'm intrigued with or really like or find interesting. And it has to be a song that has a good amount of words to it too, right? Like this song, this song wouldn't have worked if it didn't have the rap bridge and the second verse, because that gives me the space to break down some more technical things. If you've got a song that's like a opera piece where they say maybe 2 lines in 2 minutes, then what am I going to tell you?
But I think the way that you explain this, you always have a story to that song. And I always come away from watching the videos that I've learned something about an area I knew nothing about, be that string theory or quantum gravity or or the outbound probe or Evo Deep. I mean, I really like your ability to condense, and the same in the Nanobot video, your ability to condense the story down to and then have to something that's useful for people to understand and interesting for them to understand. Then you have this kicker at the end saying that and by the way, it's all biology does all this. This is great.
Yeah, well, I loved what you said about how you think about lecturing as storytelling, because I think that's what you have to do to effectively convey information. You have to put it in like that. Like that's how human brains work. We work in narratives. Even when we're constructing our dreams, might just be random firings, but we'll put it into a story when we wake up. And that's the proper way that information goes into your brain, I guess. So that's what I'm always trying to do, is figure out, if you're telling, and it's a good way to structure your ideas too, right? If you're thinking about telling a story, if you tell a good story narratively, it's never that this happened and then this happened and then this happened, like disparate events. If you want to tell a good story, it's this happened and as a result this happened. But because of something else, this happened, and there's a line through it, right? And so when I'm thinking about information, and this is something that I learned from a great talk I heard by the guys who run this channel called the Wisecrack channel on YouTube, where they do sort of pop philosophy, but this is how they think about storytelling in informational fields. It's exactly the same, and you can actually break it down even more broadly if you want, in terms of the ring cycles and the hero's journey and all this kind of stuff. If you can take a subject and find a protagonist, either in a character, the person who discovered it, or even the protagonist can be the idea itself, and you can find a line through the entire field. I think that's what, because I can't hold on to information if it's not in that format. If you tell me 10 facts, I'll forget 9 of them. But if you tell me a story that weaves the 10 facts together like beads on a string, then it all stays in my brain. I can follow it.
Yeah, and that's also, I have, we were talking about the use of magic, and I also have jokes and videos and other sorts of things in my talk. And I think part of that is also to try and have sort of not tricky things that people can grab hold of that they'll remember, and hopefully, if I'm doing something to illustrate a magic trick, to illustrate a ratchet mechanism or a motor mechanism or something, hopefully they, as long as it fits well to that the experiment that I'm talking about, then they'll remember that a lot better than if it's just a cold science lecture that I'm doing, I'm sure.
Yeah, I think I definitely don't remember 95% of the lectures that I went to in university, but the ones that I did they either had a very good story or they had a really powerful idea that I was already thinking about. So that goes back, I guess, to both of the ideas that we're talking about here.
Yeah, definitely. Yeah, I think that's one of the things that people hopefully like about molecular nanotechnology and molecular machines. It's a very powerful idea about something that's, going on now, that you can see that it can really work because of biology, and you can then think about what is that going to do for our future. Let's go and invent it.
Mm-hmm. And it's going to, as it progresses, it's going to be built up in this structure from the basic elements, and it's going to have a natural story to it as it goes.
Yeah.
It's the same way that biology does, that you can tell it from biochemistry building up and up and up.
Yeah. No, absolutely. It's going to be just like the Industrial Revolution and happened with steam engines, and then going on to manufacturing and Henry Ford and all these sorts of things. You're going to see the same sort of progression with how molecular machines impact. It won't be that in 2 years' time you'll go out and buy a packet of molecular machines for something. They'll slowly be incorporated into how we make drugs, how we build other molecules, how we make materials, included into materials that can do different things. So it'll be a gradual evolution into more and more things, I think.
Yeah, well, we'll have to see how long that takes. I have in my closet right now a CRISPR kit from a box that I got off the internet for $100 that enables me to do genetic engineering in my basement at some point.
That's just the most extraordinary technology, of course. And enjoyed your video on that as well.
Mm-hmm. Yeah. Well, that's kind of why I thought I've got to try this for myself. But it's been sitting there for quite a while. I've got to pull it out and do something with it. But people have a lot of worries about that. That kid is fairly controversial because it's a guy who just started a lab in his garage and decided, you know what, I'm going to democratize this technology and I'm going to send it to anybody who wants to do whatever with it.
Those sorts of things, worry us as scientists, I think, because it's not the sort of technology that you want people. I mean, if it's really, I don't know about this kit, but if it really allows you to do things on, important things on your own cells and things like that, then one would worry about people having access to those sorts of things. Not that they're not going to release something that's going to harm the whole population, but they can hurt themselves.
Yeah, well, this one is very basic. All I can do is, I think, turn a little yeast red. But if you can do that, there are many other things that you can do with similar access, presumably.
Sure.
Do you worry about that with people worry about disaster scenarios with nanotechnology?
Yeah, no, I mean, of course, there is this fear with nanobots that you'll have grey goo that would self-replicate and take over the world. But
can you describe the grey goo scenario for people who don't know?
So the idea of molecular machines and molecular factories from the engineering, the bottom-down engineering approach, first brought up by Feynman in Plenty of Room at the Bottom, that was taken up by Eric Drexler, a key figure in the 1980s in popularizing this idea of nanotechnology. And one of the things that Drexler hypothesized about was the possibility of having self-replicating nanobots. After all, I mean, we're saying that that we are nanobots, or that life is based on molecular machines, and we know that cells replicate. So why can that not happen with nanobots in a malicious way and have them, take over the world? But I mean, we're so far away from. I mean, it's so difficult even to make something that's just a switch that picks up a substrate from one place and put it down in another, that to get to the stage where you would have things that could really be seen as living, an artificial life form. I mean, that might come in a millennium. Who knows what the future will be? And the more that we learn about how to make artificial molecular machines, the more we learn about how life really works at the molecular level. But it's not going to be something that can accidentally happen, that someone would create nanobots that could self-replicate and take over the world. And far more dangerous things are things like CRISPR in the wrong hands, which obviously could be used to manipulate bubonic plague or other sorts of put nasty things into replicating bacteria that could create terrible weapons. But that's not going to happen with nanobots, not in any of our lifetimes for millennia to come.
So what you're saying is biology is sort of a mature technology. So messing around with that form of nanotech actually has the capability to make something that works. Yes,
that's right. And so that's definitely why one would worry about CRISPR and the possibilities that holds for nefarious activity. But I mean, as with all technology, it's not inherently good or bad. It's what people do with it. And obviously, CRISPR is going to be a force for tremendous good. And we just have to try and find ways of making sure that it isn't abused in ways that would be bad for mankind, and hopefully that will be done.
But you could worry about with synthetic nanomachines that there would be an additional danger of us not having any defenses to that sort of thing, right? Because the fact that we ourselves are in some ways a mature technology means that we've had billions of years to combat the usual mechanisms that occur in diseases and plagues and stuff like that. And you see that in antibiotic resistance, how bacteria become resistant to antibiotics very fast, but it's because we're using chemicals that have already existed in the natural world and that some bacterium has had to develop a resistance to, and then they have ways to share it and spread it around, and there's already the seed there.
Yeah. The molecules of molecular nanotechnology and building molecular robots, these are organic systems. So they're made out of the same sorts of components. They're not little shiny metal nanobots that are very alien in the sort of the elements they use. They're made out of the same sort of constituents as nylon or organic molecules themselves. They're carbon, nitrogen, oxygen, and sulfur. And the immune system works by producing antibodies, not to things that it already knows about, but to anything that's alien. So for sure, if you had a big dose of something and the immune system didn't recognize it, you would produce antibodies against that, and your immune system would work to attack it. So, I mean, there's just the molecules that we and others in this area make are no different to any other organic molecules that are used in paints, dyes, polymers, drugs, and they're definitely nothing that people should worry about. But as we've said, manipulation of actual biology, that's overwhelmingly for good, because it's going to change our whole approach to healthcare, personalized healthcare, healthcare based on the genome and individual solving individual problems. So it's overwhelmingly positive, but there's no doubt that there could be things that are not nice that could come out of that technology.
Well, yeah, it's the old Spider-Man maxim: with great power comes great responsibility.
Exactly.
So it's as the technology gets more powerful that you have to worry about it. Where do you think the first practical application of this synthetic molecular machines is going to find itself?
Yeah, there's already people who are making materials that have got these kinds of molecules, catenanes and rotaxanes in them. They're used in some cell phone coatings because the rings are thought to allow the sliding of polymer chains over each other, and so help cushion impact and have things. Those aren't really molecular machines. I think they're more new materials, and I think that that's going to be an area where these sort of architectures are used. I would say that the most likely area for molecular machines to first have influence is surface properties, because molecular machines at the moment are extremely lengthy to synthesize, just as work intensive to synthesize just a very tiny amount of them. So it's hard to think that they're going to be used in bulk for anything. They would just be so expensive. But if you had them as surface coverings, so for example, you had a material that was just a very simple molecular machine that switched properties from being, say, sticky to non-sticky, so you could have something that could be an adhesive, shine UV light on it, and it would switch off that adhesive properties. You're already seeing sort of sensors based on molecular machines. You show some in your video of the logic gates, and those are already used in diagnostics. AP De Silva from Queen's University in Belfast has developed those Boolean logic gate systems for sensors, and those are used in diagnostic kits in ambulances. So that's great. That's technology that's really being used to save lives and help people already.
Wow, I didn't know that those logic gates were already being used in any system. I only knew of them in little vials being shot with one type of light and emitting another type of light very abstractly.
Those are already being used to detect. You can have a logic gate that detects, say, that only is fluorescent when there's sodium is lower than a certain value and potassium higher than a value, or whatever, something like that. Where the ion concentrations are diagnostic of a particular condition. And say some of those kits are already used in detection systems that are used in ambulances at the moment.
That's one thing that always amazes me about new technologies and new information of any kind, is just how quickly people find ways that it can impact some completely different field that you wouldn't expect. Like there are so many possible connections between fields that it's one thing that I don't know. I think is a better argument for basic research, like the kind of stuff you're doing, than even what people usually say, which is that, well, it's a twist on the usual argument. Usually when people say, why should you do basic research? It doesn't seem to have any use. People say, well, look at all the research in the past and look at the uses it's come to now. Yeah. But just like that.
I think you're absolutely right. And the other thing that this shows up is the incredible impact on fields that other fields have on. And we've talked about molecular machines that depend upon ratchet mechanisms that were developed by physicists, and it's it's inspired by some of the things that we do are inspired by the biological systems. But then you've got Boolean logic gates from informatics and computer systems, but those are the sort of systems that need to be brought into programmable molecular machines in order to understand how you are going to use them in a sophisticated manner to do complex tasks. And as we've seen, they can be used in sensors. So also, I think another important thing, we become more and more specialized in what we become expert in. The people in my group are experts in being able to construct molecules. But unless you have this general understanding of other fields as well, having that general understanding of how other fields can impact on what you do can really make a huge difference in advancing all kinds of parts of science, I think.
Yeah, I hope that's sort of breaking. Like my hope is that the connectedness of the world will spill out into the connectedness of science. And one of the things that I noticed that I really like that you're doing, like on your website, which is catenane.net, I think, if people want to go and visit it. But you have all these papers that you've published that are just there freely available. And I so wish that every scientist would do that because you actually do have the right to put your own paper up wherever you want for people to see it. But so much of this new information right now is behind paywalls, or you have to be part of an institution to gain access to it. And even a lot of like lower ranking institutions don't have access to, the 500 journals you would need to make these sorts of connections. And maybe there's something that already exists that solves your problem, right?
That's why it's already so important to have open access publishing, and that's coming on over the last 5 years, and that's going to be how everything is going forward. I mean, it was started by the NIH and other major players in the United States who insisted that research that they published was made open access, and then other countries such as the UK and Canada also have these policies as well now, so one does that. One of the other things that we try and do on our webpage is we try and have simple stories, simple explanations of the sort of scientific highlights. When we publish a paper, we can't always have a brilliant musical video to tell the story, but we can try and explain what we've done in a way that hopefully people can appreciate and understand what is going on in the field, and get something from it that hopefully they find interesting. There's not hyped as well, because obviously there's a tendency to have things hyped in the media, and we don't want to do that. We want to try and explain the science facts, not the science fiction of things that are going on.
Yeah, and you want to be able to make these interdisciplinary connections. I think what you want to do is take as much of your expertise as possible and keep it in a black box, but have an interface that people from other fields can understand, right? So you give them a story that is in fact accurate on the functional level where they would need to apply it in their own field.
Yeah.
And I think...
Yeah, no, that's absolutely right. We don't want biologists or physicists to try and make our molecules, but we'd love them to understand what we can do and what we can't do yet, so that maybe they can find some either understanding, maybe it helps understanding of some processes in biological machines, or even they can suggest to us mechanisms or things that it would be cool to build into synthetic molecular machines, because this is what a biological machine does, or how a ratchet mechanism works. Can we do that? I mean, that's how we learned how to build all the different kinds of molecular motors that we developed, was just learning from what physicists have done and taking their blueprints and applying them to molecular design. So it's all about taking, I think also, or a lot of great scientific progress comes from taking a discovery in one area and applying it in a completely different one, just like you were pointing out.
Well, that's what in a way, that's sort of how I think about this whole project that I'm doing, because I am doing it in many senses to popularize science or to explain science to other people. But part of what I feel like I'm doing is chunking fields of science in a way that I'll actually, once I get to the end of going through all of them, or as many as I can get to, that I'll actually hold on to the information that I gathered at the time. So it's like having a logbook where I had to synthesize it into the most compact form that it could, so that when I'm done, it can actually all fit in my brain and I can apply connections from one place to another. Because I have found that, like, even working on this video, I was noticing a lot of similarities between the stuff I was working on here and the Evo Devo video that I did, because that's a field where there were all these connections coming in from physics and from computing as well, and these logic gates through transcription factors on DNA. And now I'm finding that now I'm going on and looking at computer science, and I've already got this background in I had to learn a whole bunch about Turing machines to understand that one part of this video with the people trying to do very basics of molecular Turing machines. And that's like, I hope that I don't know, if I can accomplish that project, then hopefully I can give other people a scaffold to do that as well. You know, you can have a repertoire of songs that you go through, and it'll actually give you something to build entire fields of knowledge on that you can actually keep. Because I get really worried about losing all the information I have. I've forgotten 99% of what I learned in my degree, I think.
Yeah, that happens to all of us. But also the way that that you're able to do it and to tell the story in the videos. For example, the Evo Devo one was so cool that it got me to go and read Sean Carroll's book. Because I thought that was so interesting, and also for me it was fascinating to see the molecular machines being used, such as the how the vertebra of the snake was done by speeding up the clock. So all these sorts of things, I find incredibly interesting and useful for the stuff that we do in a general sense for understanding. If one day we make molecular factories. Maybe those are tricks that we will be able to use to have ways of speeding up processes to have one thing happen and not speeding them up to have something different happen. Those sorts of that's a concept that's clearly used by biology that I didn't know about. That perhaps we can think of adopting one day down the line in how to use synthetic molecular machines to do different things.
Well, I would be totally honored if something that I mentioned in a song impacted the future of your work. That would be amazing. My camera battery is running low, so I think we're going to have to wrap this up. Is there any other message that you'd like to give to people, or if you'd like to tell us where we can learn more, where we can follow you, that sort of thing?
Just as our web address is given at the on the bottom of the link of the nanobot video, www.catenane.net. And thanks so much for doing the video, Tim. You did a great job, and thanks for having me on to talk with everyone today.
Yeah, no, this is a fantastic conversation. I'd love to do this again.